Kia ora. I'm Ziyun Wang from School of Chemical Sciences, University of Auckland. Today, I'd like to share our attempt on liquefying electricity. I would like to begin with a question. How many of you prefer an electric car over a gasoline-powered car? I suspect most of you see electric car as the future. Consider this image. It showcases an electric car that appears greener than a traditional gasoline vehicle, which often contribute to pollution. However, even after switching to an electric car, you might find yourself missing certain aspects of gasoline-powered vehicles. Why is that? Here we compare two cars, a Tesla Model 3, which relies on a 480 kilogram battery to achieve a 629 kilometer range, and a conventional gasoline car that need only about 33 kilograms of fuel to cover the same distance. Beyond that, refueling a gasoline car is also much faster than charging an electric one. To understand why this is the case, we look at two key matrices, the gravimetric energy density and the volumetric energy density. Effective energy storage demands on energy carrier that is both compact and lightweight. As you can see, battery lag behind on both measures. If we plot these two matrices on a single graph, the choice of energy carrier becomes clear. Diesel and gasoline offer the best balance between gravimetric and volumetric energy density. However, we all know that fossil fuels are non-renewable. But what if we make them renewable? Electrochemistry explores the interplay between electricity and chemical reactions. By leveraging electrochemistry, we can convert CO2 from the atmosphere into valuable chemical feedstocks or fuels. It is similar to charging a battery. We charge the CO2 molecule, store the renewable energy in the chemical bond. As a result, the produced fuel are renewable and free of impurities, thereby reducing air pollution. This process offers an opportunity to close a carbon cycle, but it also presents significant challenges. Think about like playing with Lego blocks. We need a building block to construct chemicals and fuels. We obtain the building blocks from CO2 and water, while electricity drives the reaction. The final piece is a catalyst, which acts like the hand that assembles the Lego pieces. The key to success lies in design effective catalyst. Design catalyst for CO2 reduction is challenging for two main reasons. First, the CO bond is very strong, making it difficult to activate. Second, the building block can form many different products, so getting the right one is hard. At Auckland, we take an alternative approach to catalyst design using computational chemistry and artificial intelligence. We start with fundamental definition of a catalyst in a reaction where reactant X and Y form product Z. The process without a catalyst requires a high activation energy. By introducing a catalyst, the overall activation energy is lower. If we can calculate the energy barrier, we can reduce the need for time-consuming experiment. Using computational chemistry and AI, we can virtually test thousands, even millions of catalysts simultaneously. Last year, using computational chemistry tools, we identified an outstanding catalyst capable of effectively converting CO2 to formic acid. Our calculations also reveals that the catalyst remains stable even under acidic condition. Our experimental collaborators validate our findings by demonstrating the first ever long-term stable acidic CO2 electrochemical reduction to formic acid, a breakthrough published in the prestigious Nature journal. This work has gathered significant media attention, including coverage by TV3 News Hub, Radio New Zealand, UA News, and other 21 media. Notably, this article ranked in the 98th percentile for public interest among articles of similar age. Is this the end of the story? Why does CO2 have such a big impact on our climate? CO2 makes up only 0.04% of our atmosphere. Thus, even a minor change in its concentration can create a significant effect. That's why it might be smarter to focus on something far more abundant, nitrogen. By converting nitrogen into ammonia, we can tap in the nitrogen cycle for energy storage. Last year, we explored all possible pathways from nitrogen to ammonia and designed a system capable of converting air into ammonia, which is a potential renewable fuel source. This breakthrough could offer us an opportunity to shift from the carbon cycle to nitrogen cycle. There is even better news for New Zealand. As an agriculture-heavy nation, ammonia plays a crucial role in our economy. With our device that can convert air into ammonia, we can envision a future where KV farm operate devices powered solely by solar cell to produce ammonia on site. I hope our research at University of Auckland contribute to a greener future and make the world a better place. Thank you all for your attention.